Hello everybody, and welcome back to my basement. I am here to finish lecture 6 and example 6 in PSQF 6242. We're doing it offline in my basement. I'm going to be starting on lecture 6, slide 15. Okay, and we're back. So just to do a little bit of review relative to where we left off, we've been talking about how to fit models that examine moderation via an interaction term with two predictors. So in this example, we are predicting student GPA from a fixed intercept beta 0, the so-called main effect, the fixed slope for the effect of parent attitudes, which has been centered at 3 near the middle of its range, the fixed slope main effect for the effect of parent education, centered such that 12 is the new 0 for 12 years, and then the term that we're focusing on figuring out what to do with is this beta 3 interaction term that does two things simultaneously. It allows the effect of attitudes to vary as a function of education, and it allows the effect of education to vary as a function of attitudes. And so one of the challenges with these models is being able to describe it to your reader, and the best way to do that is to be able to build a figure that illustrates the predictions of the models. So what we're looking at here is code in SAS and Stata to create model predicted outcomes. So if this was my model and I wanted to be able to show the effects of attitudes in education and how they interact, then I would create predicted outcomes that include all model fixed effects. So when you are trying to compute y hat, then you are trying to make predictions for prototypical values of your predictors. They do not include the residual, so this is only using the fixed effects. But for instance, if I had wanted to create a predicted outcome for somebody who has a high level of attitudes about the importance of education, so a value of 5, as well as 16 years of education, then to fill in this equation with those corresponding values, then I would put a 1 next to the intercept, because what I'm saying is I need 1 beta 0. Then relative to attitudes of 3 as the 0, an attitude score of 5 is 2 higher, so I have a 2 here. And relative to education of 12 as the 0, education of 16 is 4 higher, so I have a 4 here. So the words actually refer to the betas that are going to be estimated as part of the model. The values refer to the multipliers that go in parentheses that express the values of the predictor for which we're creating an expected outcome. Last but not least, we can't forget our interaction term. Beta 3 is represented by the attitudes by education interaction phrase here, and we have an 8 here because 2 times 4 is 8. Did another example with attitude equal 1 and education equals 12. We need an intercept. A score of 1 is 2 less than 3, so that goes -2. We want it for education equals 12, so that drops. And -2 times 0 is 0. So this middle line would only be a reflection of someone's score on attitudes. The effect of education has been zeroed out to the model reference. The last one, which we didn't get a chance to do, if it's attitudes equals 3, then what would go here, let me go ahead and fill it in for us, is a 0. Education equals 20. 20 is 8 more than 12, so I would put an 8 there. And 0 times 8 is 0. So that's what it would look like. And the same values would go down here into the Stata version of the same code. if we want to create the slope according to the model for a predictor that is part of an interaction term, so what is known as a simple slope or a simple main effect or a conditional main effect, then we follow a three-step process to determine how the model tells us how to find the fixed slope. The first is to identify all of the terms in the model that contain the slope of interest. We then factor out the variable the slope is for, and the linear combination that's left provides us with the ingredients for how to find that slope. We would then need to ask the software to calculate what the slope would be for the particular value of the moderator, and as well as provide a standard error for that linear combination. So for instance, if we work with the same linear model here with an education by attitudes interaction, first step is to identify all the slopes. So if what we're trying to get is the slope of attitudes, we go through the equation, find all the places that have attitudes in them, and only bring forward those terms. So we would have beta 1 times attitudes plus beta 3 times attitudes in education. Likewise, if we were trying to do the education slope, we would go through this equation and find only the terms that have education. So we would bring down beta 2 times education plus the interaction term. Next step is to factor out the predictor of interest to find the linear combination. So if we take, for instance, attitudes out and stick it in back here, then we're left with beta 1 plus the interaction term beta 3 times education. These are the necessary components to get to the attitude slope. So at a minimum, we need the main effect of attitudes. Beta 1 is going to provide the slope of attitudes whenever education is 0, because that's when this extra part drops out of the equation. Otherwise, we have to know the value of education for which we want the attitude slope. Likewise, if we factor the education variable out, stick it in the back, the linear combination is the simple main effect of education, which is specifically when attitudes is 0, because that's when the second term drops. Otherwise, we need to know the value of attitudes for which we want the education slope. And if you're interested in knowing how the standard errors get computed, here is the information needed for those. They are a function of the standard errors for the main effect, as well as the covariance between the standard errors, from the main effect and the interaction term. So this is not fun to compute by hand, which is why our friends estimate statements in SAS, Lincom statements in Stata, and other similar procedures are helpful. So then we went through this process to try and request model predicted simple slopes for different kinds of people. Just to remind you, these are the ingredients that we just determined. This first equation tells us how we get the attitude slope, and the second equation tells us how we get the education slope. So if we want to know what the attitude slope is for somebody with education equals 10, we do not need the intercept because beta 0 is not in here, because beta 0 has nothing to do with attitudes. We do need one beta 1. We do not need any beta 2s. And the number of interaction terms we need is based on the value of the moderator of education. So if education equals 10, that is 2 less than the 0 point of 12, which is why we have a negative 2 here. Likewise, if we wanted to have education equals 18 instead, that is 6 more than the 0 value of 12 here, so we put a 6 here. The exact same idea, but in the reverse direction, is what we need to compute an education slope. So then we'd be using the second list of ingredients here. We still don't need an intercept. We do not need a main effect of attitudes because we're trying to get the slope of education. We do need the main effect of education, and we do need to give the value of the moderator, which in this case is attitudes. So attitudes of 2 is 1 less than the centering point, so that's why this is -1. And attitudes of 5 is 2 more than the centering point, which is why this is 2. So that's all well and good, but the idea that you can request simple slopes for different values of the moderator is more useful when your moderator is categorical than when it's quantitative. So as in a different example, let me exit out of this so that I can do some typing for us. Here we go. So if I wanted to do this equation right here, how do I get the age slope? Well, I'm going to need 1 beta 1 and I'm going to need the interaction term. And I'll take that part out because we've factored that out. So if I want then to compute the age slope for different values of my moderator, so using this equation, I would need 1 beta 1. And in the variable for women, if it's for men, then that's a 0. And, oh wait, excuse me, I'm screwing my own thing up. It's a 0 because 0 refers to the lack of a beta 2 in this case. It's one step ahead. So we don't need a beta 2, but we do need a beta 3. And the value that goes in for the moderator is 0 because that's what it means to be a man in this variable. Likewise, if we wanted to compute it for women, we need 1 beta 1. We still don't need any beta 2s, which is why that's a 0. And we do need 1 here to fill in for the moderator. But if we go the other way, so this beta 3 interaction term, one of the things that it does is tell us that the age slope differs between men and women. That's what it means, the difference in the age slope for women relative to the age slope for men. And that interpretation of gender as the moderator is consistent in trying to determine what the age slope would be at each value of that gender moderator. But what if we go the other way? What if we are a researcher who is interested in gender differences and we want to look at how gender differences vary by age? Well, that's a different story. Now we start with beta 2, and we still need the interaction term, but we need it to multiply the moderator of age instead. So now, make this a little bit prettier. There we go. Now I have the ingredients by which to form the gender slope. So if I go down here, I don't need any beta 1s, so that's a 0. Same is true here. There you go. I do need a beta 2. Put those here. And then the value that goes in here are the ages for which I want the gender simple slopes. So if I want age 80 relative to a centering point of 85, that would be a -5 here. And if I want age 90 relative to a centering point of 85, that would be a +5. But this is just 2 potential ages of what is actually an infinite list, right? I could ask for every possible age at which we have someone in the data set. So it becomes less useful to try and talk about simple slopes when there's many possibilities for what they could be. So as an alternative, I want to show you something called regions of significance. So this approach I describe with references for its origination in Chapter 2 of my longitudinal book that's on your reading list for 6242. The idea is that rather than asking what is the simple main effect of gender at a particular age, we can turn the equation around to find the boundary ages at which the gender effect becomes non-significant. So we know that the estimate divided by the standard error for our simple gender slope forms a t-test, t-value. And if we use infinite denominator degrees of freedom. For convenience, you could put in whatever number you want here, but that's what's typically done in this case. So we're treating t as a z, in other words. Then we know that t needs to be greater than 1.96 in absolute value if we're using an alpha of 0.05. So we work backwards. So if we know that t is made of the estimate divided by the standard error of the estimate, so the square root of the variance for the sampling variance for the estimate, and we know that the gender slope is created using this equation, that means the variance of the slope estimate is created using this equation. We need to get the asymptotic covariance matrix to be able to get this term right here, the covariance for the slopes of the gender effect and the interaction term. So this is the idea that what the standard error is is related to what the standard error is for the interaction term. So there's actually a full matrix that has the standard error for each fixed effect in the model squared on the diagonal as the variance, and then there are covariances between them. This is not something that we typically would need to look at, but we do need to get the covariances to be able to compute this formula. So then we can figure out what the values are of the slope estimate where t would be significant. And so running this same data set, this example, through, I have a SAS macro that I wrote that does this. I also put this into an Excel sheet. I'm sure you can find R packages and whatnot that do regions of significance as well. But here's our equation. And let's say that our results are that we have a simple gender slope of minus 0.53 at age 85. So that's what beta 2 means, because that's when age is 0 and this part would drop. And let's say that we found the standard error squared was this number. The estimate for beta 3, the interaction term, is found to be minus 0.11, and I note that this is unconditional because the interaction term is the highest order term. There's nothing else in this equation that contains both age and gender. And it has a standard error squared of this. Let's say that we found the asymptotic covariance matrix to get the covariance between these two slopes. And the results, once you plug it into the formula, came out to be 60.16 to 79.52. So what that means is the gender effect is predicted to be significantly negative anytime above age 79. So that makes sense in context of the results that we got where the gender effect was significant at 85. The interaction term is making it more negative as age increases. So for every unit older someone is, the gender difference is expected to be greater, more negative, by 0.11. That means that the gender difference is also predicted to be smaller as age decreases. So if we go back down, then it becomes less negative in younger people. And so once we hit 79, that's when the negative gender slope would become non-significantly negative. It would remain non-significantly negative all the way down until age 60, at which point less negative, less negative, less negative turns into more positive. So non-parallel lines eventually cross and the differences change directions. In this sample, however, if we didn't have anybody who was younger than age 60, then we wouldn't necessarily worry about this result. So you can use this approach to figure out at what points along the moderator a given simple slope shuts off and turns on, and in which directions. So there's the big summary, the idea that we can test moderation, or the extent to which the effect of one predictor depends on the value of a moderating predictor. The particular form that I've showed you in this lecture and example uses only one interaction term because each of the variables used as predictors that are interacting, their slope is characterized by one slope. So we only need one interaction. In the next lecture and example, I will show you what it would look like to have interactions among variables that are characterized by two or more slopes, such as when the variables are categorical or when the quantitative variables have nonlinear effects. Then the interaction terms between them require more than one slope as well. We have to keep in mind that main effects are no longer just marginal main effects. Instead, they are the main effects of a predictor specifically, conditionally, when any variables that they interact with are zero. And for that reason, we want to make sure that zero is a meaningful value in every predictor that goes into our model. And the rules that we learned to interpret two-way interactions, that they take the main effects and make them either more or less positive or more or less negative, those hold in interpreting higher order interactions as well. So for instance, three-way interactions would take two-way interactions and make them more or less positive or negative. So we will get a chance to see such examples later in the end of Chapter 2 if you want to read that. Otherwise, stay tuned for longitudinal modeling in the spring, in which we will see three-way interactions. So with that in mind, let's go back and finish example 6. So just to remind you all, this example is from Chapter 2 of the book. The model that I'm going to show you today is what was featured in the middle section of Chapter 2, where we're looking at predicting cognition as measured by the information test from age centered at 85, grip centered at 9, gender with men as the reference, and dementia status as a categorical predictor in which the none group is the reference, and we're comparing none to future and none to current. So the first step in any analysis is to make sure that you have all of the variables that you need. So this is the process here of centering quantitative variables such that 0 is meaningful, and I picked these values because they were near the means of the original predictors. I then created 2 new dummy codes because I have a 3-group variable. So if I had 4 groups, it would take 3 dummy codes. If I only had 2 groups, it would only take 1 dummy code. Added labels, did the same thing here in Stata. So the gen statement to create new variables when you're centering quantitative variables, as well as a combination of gen and replace to do the dummy coding. We've gone over that before. And this example started with a main effect. So we're looking at the marginal unique effects of each of these predictors. So each is controlling for the others. That's what I mean by unique. And marginal because there are no interactions yet in the model. So we looked at that, determined that each of these things was significant in terms of predicting cognition, made a picture in which I'm showing the effects of age and grip strength, and the parallel lines indicate that they do not depend on each other. So there is no interaction. The effect of age is regardless of grip strength and vice versa. Here's the same version in Stata. Notably, margins is a very nice and quick way to get a range of predicted outcomes, and margins plot throws them into a picture for you. Very slick. In class, we went over this second model because it is featured in your homework 6 for 6242, so we spent some time on that. We added 2 interaction terms, one for gender with age and one for gender with grip strength. In terms of the rest of the code, this estimate statement is getting the model-implied difference between the non-reference groups. So none versus future and none versus current is going to be given by these 2 slopes directly. This line right here asks for the difference of future and current. Contrast lumps those 2 dummy codes back together again to give me an overall effective dementia group, or what's known as an omnibus effect, as well as an effect size. And this contrast is used to test the simultaneous addition of those 2 new interaction terms. So whether or not those 2 things work together to significantly increase R square. Contrast will give me an F test for the change in R square. We then went over simple slopes, and this is how one would get an age slope for gender as a moderator. So following the same logic that we did in the slides, we first find all the terms that have age in them. We then factor age out, and the root of what's left here gives us the ingredients. We need 1 beta 1, and then beta 6 gets multiplied by whatever value for gender we're putting in here. In this case, men are 0 and women are 1. Do the same thing for grip. So we have the grip main effect and then the moderator for gender of that. And then this is how I created predicted values for men and women with high and low values of age and grip strength to be able to make a picture. Same thing in Stata. My interaction terms here are defined using a hashtag if you are under 40, or what we old people call a pound sign. LINCOM is the analog to estimate for asking for the model-implied dementia group difference. Test statements are the analog to contrasts. They are used to first lump together the two dementia contrasts to get an omnibus effective group, as well as to test the change in the R-square relative to the main effects model that comes from adding in these two new interaction terms. Then we have LINCOMs for simple slopes. Stata also has a thing in margins called dy/dx that gives you simple slopes. I'm not showing that here, but I will show that in future examples in the longitudinal class and others. Same logic for getting simple slopes of grip strength by gender, and then margins to be able to get predicted values for high and low values of age and grip strength, as well as men and women. And this gives us a range of values, start at -5, in increments of 10, go up to 5. So that's a nice feature of that. So then we looked at the output. Overall, the model with 7 slopes does significantly predict cognition. It does so by capturing about 28% of the variability in cognition, and 88 is the amount of variability in cognition that is left over the residual variance, or the mean square error term. We talked about effect sizes for these things. There are semi-partial eta squares that you can refer to for individual terms or for groups of terms. Stata makes this harder to get those, which is why we're not doing those in homework. And then we walk through the model in class. So if you're interested in a detailed interpretation of this model, please visit part 4, video part 4. This is going to be video part 5. And then we talked about the importance of making pictures. So then we're left with the example results section. Because neither of these terms contributed significantly to the model, and jointly they did not as well, resulting in a change in R-square of 0.002, we would drop them from the model and move on. So this is the model that I want to focus on in this video. This is the model that is described in section 2 of chapter 2 in great detail. I wanted to show you how to do this in SAS and in Stata. So we removed the interaction terms of age with gender and grip by gender, and we're including an interaction of the two quantitative variables, age and grip. So just one new interaction relative to the main effects model. Because there's only one new interaction, I don't have to ask for an R-square change test. If this new single interaction term is significant, then I know the change in R-square is significant. There's a one-to-one correspondence between the change in the model and this one slope. Instead, I'm making an example here of how to ask for a combined test of age, grip, and their interaction. So lumping those together to talk about their contribution to the model as something that may be of interest. So we're going to have simple slopes for age and for grip, two different ways. So first, if we want to think about the effect of age as the term that we care about, and then grip strength as the moderator, we can calculate age slopes for different levels of grip strength. So how do we do that? We go up to the equation. We find all the terms that have age in them. Or, yes, age in them in this part. So that's just 2 in this case. We factor out the common age term and stick it in back. And here is the set of ingredients that's going to give us the age slope for different values of the grip moderator. So for instance, if I wanted to have age slope at grip equals 6, so I picked 6 because that's roughly -1 standard deviation of this variable. That's commonly used as what a prototypical low value would look like. So I need 1 beta 1, so that's that, and I need the value that is going to multiply the beta 6 interaction. So the beta 6 interaction is referred to by these words, and 6 is 3 less than 9, so that goes here, -3. If its grip strength equals 9, that would be 0. So that means technically this line is redundant with the output that I would already get by default, because the age slope at grip equals 9 is exactly what beta 1 means. That is the point at which this second piece would zero out and not contribute. And then lastly, grip equals 12 as a prototypical high value of the moderator. 12 is 3 more than the centering point of 9. So these values of grip as the moderator are arbitrary. I could have picked any value that I wanted. The idea is to try and help readers understand the pattern of the interaction, and one way to do that is to talk about what the effect of the predictor would be at low, medium, and high values of the moderator. So that's the strategy enacted here. If I wanted to spin it the other way, the effect of grip strength is the predictor that I care about and age is the moderator, I go up to the equation, I find all the terms that have grip, I factor grip out, and then here is what provides the grip strength slope for different ages as the moderator. So in this case, I picked ages 80, 85, and 90. I fill in a value of the moderator that is consistent with the centering. So 80 is 5 less than 85, 90 is 5 more than 85, and the ones in the first column here correspond to needing 1 beta 2 in each of these simple slopes. And then down here, I am creating predicted outcomes for prototypical low, medium, and high people for age and grip strength. Note that these are what's known as adjusted means because I am holding constant the variables that do not have interactions in this model, gender and dementia. The next example, 7, will show you how we would fit interactions with those. So when you're creating predicted outcomes, you need all of the terms in the model, otherwise leaving them out sets them to 0. So I need an intercept. I need the value of age for which I want the prediction, the value of grip strength for which I want the prediction, and then -5 times -3 is positive 15. So we're just filling in the values of the predictors for which we want the y-hat directly. So we have age 80, age 85, age 90, and then 6, 9, 12 for grip strength with corresponding results when you multiply those together to create the interaction term. And I am saving this little table to a data set so that I can use it to make plots with. Here's the corresponding stata code. So here's the new interaction term. Here's the corresponding test statement that would lump age, grip, and their interaction together if you wanted a test of those 3 things simultaneously, just as an example. Here's the code by which we would get simple age slopes. So repeating the logic from above, find all the terms that have age in them, factor age out, and here's what's left. And here are the lincoms that would correspond to grip of 6, 9, or 12. And I did do dy dx. I forgot that I had put that in here. There's a little bonus for you. So this one line actually replaces all 3 of these subsequent lines. The dy dx command gives you simple slopes for the value of the predictor variable that's listed in parentheses at a range of values of the moderator. So you could ask for a whole bunch of these things in one line by asking for the slope of age at different levels of this moderator in parentheses. Likewise, we could get the simple slope for grip strength, and here is how you would get that as a function of age. So we swap out, if we are thinking of grip as the predictor, that goes in the dy dx, and age as the moderator would go over here. And the values then would be grip, meaning we need 1 beta 2, and then the values attached to the interaction term correspond to age as the moderator. Dy dx, by the way, is derivative language. So the derivative with respect to, I think, is where that came about. And then margins to create predicted outcomes. So for a range of age, for a range of grip strength, and then holding my other 3 predictors constant. And make some pictures too. So here is the result of our model. The first table tells us on the whole how the model's doing. Does it significantly predict cognition? Yes, it does. The 6 slopes do work together to create a significant model. The model accounts for 29-ish%, so about 2% or so relative to the main effects model, higher. Here are the effect sizes. I note that grip and age are each conditional, so these are the effect sizes that correspond to the simple slope of each of these things when the moderator is 0, meaning that these effect sizes would change as a function of centering. So that's what okay but conditional means. And yes, this is me, Proc Lisa, trying to help you understand what this is. This is not SAS being nice to you. I note that these two terms, because they share a common reference group, these semi-partial eta squares are not valid. They need to be combined into one combined term for both of them to be able to describe the amount of the R square that is due to dementia group. So that is one of the reasons why I asked for that, which was provided by contrast, the set of those two dummy codes that together differentiate the 3 means accounts for 17% of the variance. So we only got about 29 altogether, so the bulk of that is due to dementia group. The new interaction term, which is unconditional because there's no other terms that contain both age and grip, accounted for about 1% more variance or so. So I was trying to do the math off the top of my head. Here's the precise amount. Is that 1% of the variance enough to say that we need to keep this term in the model? That is given to us by the test of that new interaction slope, and lo and behold, it is significant, so we would want to keep it. The fact that this new slope is significant means that the change in this R square relative to the main effects model without the interaction term is significant as well. So if we want to go through and focus on these effects, I note that the intercept has the same interpretation as it's had in every model in this handout. It is the expected cognition when your predictors are 0, which is for an 85-year-old with 9 pounds of grip strength who's a man who was not going to get dementia. The effects of gender and dementia are marginal because they are not part of any interaction terms. So the gender difference is unconditional. It's for everybody. Likewise, the dementia group differences given here are unconditional for everybody. So we can focus on the simple main effects of age and grip strength as well as their interaction. So age 85, because it's part of this grip strength interaction, we'll go this way first. This is the simple slope for age, specifically when grip is 0, which given our centering strategy happens for grip strength equals 9. So for people of middle strength levels in this sample, for every year older they are, cognition is predicted to be lower by 0.33, and that is a significant effect. So older ages are associated with lower outcomes for people with grip strength equals 9. Specifically, if I want to then look at the interaction term as how grip moderates this effect of age, then I would say for every unit higher grip, so for every unit stronger you are, this age slope becomes less negative by the interaction term of 0.12. So I'll say that again. This age slope of minus 0.33 is specific to when grip is 9. For every pound stronger grip than 9, this negative age slope becomes less negative. It's a positive interaction coefficient. It becomes less negative by 0.12 per pound of grip strength. So if we put that into more common language, we would say that the negative effect of age is weaker in persons who are stronger. More specifically, the slope of minus 0.33 becomes less negative by 0.12 per pound. And so the simple slopes can help us conceptualize what that would look like for prototypical values of grip strength. So for instance, down here, I have those. The middle one at grip strength equals 9 is exactly what was given by the model. The slope for grip strength equals 6 is more negative because grip strength is lower, and the slope for grip strength equals 12, the age slope for grip strength equals 12, is less negative and actually heading into positive. So it looks like age does not matter amongst people who are relatively strong. So at about 1 standard deviation above the mean in this grip strength moderator. Age does matter in people who are middle, and age matters more in people who are weaker. So this is a snapshot then of how the age slope changes as a function of our grip strength moderator. Somewhere between 9 pounds and 12 pounds, age stops mattering significantly. The negative slope becomes non-significantly negative. So we would want to know, we could use regions of significance to figure out exactly where that happens, somewhere between 9 and 12. If we followed grip strength high enough, we would see that this negative slope that starts to become positive would become more and more positive as grip increases, and at some point will become significantly positive. So the regions of significance would tell us the grip strength value at which it becomes significantly positive instead. So we'll look at that in just a minute. If we go the other way, let's start with grip as the moderator, which has a positive significant slope of 0.62. That is specifically for somebody who is 85. With age as the moderator then, we would say that that positive grip strength slope of 0.62 for an 85-year-old becomes significantly more positive by 0.12 per year of age. So the effect of grip is stronger, is more positive in older people. The effect of grip of 0.62 is specific to an 85-year-old. It becomes more positive by 0.12, the interaction per year of age. So we could go down here and look at the grip strength slopes then. And it was significant at age 85. That's what the model just told us. It becomes more positive as age increases, and so it's still significant at 90. But look at what happens at age 80. So somewhere between age 85 and age 80, this grip strength slope becomes non-significantly positive. Somewhere between the two here. And if we followed this pattern into age 75 and age 70 and so on, this positive slope would eventually become negative and significantly negative. So we would want to find the regions of age for which the grip strength slope would be positive and heading down into when it would turn negative. And here are the predicted values that the model creates. Here is the corresponding stata output that tells us the exact same information, except the intercept is last, much to my chagrin. And here are the margins from stata and the pictures it produces. And here is here are the effect sizes. So in stata, in order to get an effect size, for one term that is a semi-partial eta square, you have to estimate the model without it. So for instance, P-core gives you semi-partial eta squares for, I made an interaction variable so that I could include that in the model. To get what it would be for dem group, since I have to lump those two things together, I fit another model without it, and then used this sums of squares formula to compute what the difference in the sums of squares would be after adding dem group back in. So this is from the full model, this is from the reduced model without dem group, and this is from the total either way. So that's where I got the same value as what SAS had given me. And this is the same thing for testing the contribution getting the effect size rather for the contribution, the joint contribution of age group and age group. I kick them out of the model, see how much the sums of squares went down by, and then plug that into the formula instead to get a total semi-partial eta squared for those three terms of about 0.06. So those are the results that SAS spits out automatically that you have to work a little harder for to get ATS data. And here are the plots. So we looked at these actually at the end of the last class in video 4. And just to go over these one more time, I have age as the predictor and grip as the moderator over here on the left. And so the red line is the effective age that's given directly by the model. The green line for grip strength equals 6, and the blue line is for grip strength equals 12. And what this is showing is, actually, no, I got that backwards. Can't see the colors on my own thing here. 12 is on the top and 6 is on the bottom. My bad. So what this is showing is that the negative effective age, so the slope of the red line is negative that we found at 85, becomes less negative as grip strength increases, and it becomes more negative as grip strength decreases. So to put it more colloquially, age matters less in people who are stronger. To emphasize the same interaction term from the opposite point of view, I plotted grip strength on the x-axis for age as the moderator instead. And so in this case, the red line is given by the model as the simple main effect of grip when age is 85, and this plot is showing that as age increases, the effect of grip becomes more positive. So grip strength matters more in the 90-year-olds than it does in the 80-year-olds. And the estimate statements and lincoms that we got used to get the simple slopes would give us p-values that correspond to each of these particular slopes. So here's some additional material. This is using a different procedure in SAS to, it's called proc mixed, which we will get to know in the longitudinal class, stands for mixed models. And the reason that I had to switch to that procedure is to get this option right here, COV-B, the asymptotic covariance matrix of the fixed effects, because I need that to be able to compute the regions of significance for the age and grip strength interaction. So most of this is the same. So if we just look at this core piece right here, this is exactly the same as proc-GLM. There's some additional options related to output and what it says here. Method here refers to the use of residual maximum likelihood, which is the same thing as least squares. So it's doing the same thing that proc-GLM is doing. It's the exact same model, just with a different procedure that allows us to have slightly different options. And I am saving the solution for fixed effects as well as the asymptotic covariance matrix given by COV-B because I've written a macro program that uses that information to compute regions of significance. Stata gives an option in their regress. It's SStat, VCE. SStat is like things that you can ask for after estimation, and VCE is the analog to COV-B, the asymptotic covariance matrix. So that is how you would get the same information to be able to compute regions yourself. This is the DAT table. So this is a table we're not used to seeing. It's rarely of interest, but this is the asymptotic covariance matrix of your fixed effects, where the values that are on the diagonal are the standard error squared for each of these fixed effects. So they represent the sampling variance, how inconsistent each of these would be expected to be across repeated samples in a squared metric. And then the off diagonals here give us the covariances between these fixed effects. And so I've highlighted the ones that are going to go into the formula for regions, which you can use the Excel spreadsheet that I posted as part of this example, or you can use my macro. So in SAS, you can write little routines to automate different procedures or calculations. And what I did is write a little routine where you would just tell it what information to use inside the routine, inside parentheses here. These are known as arguments to this function. So it wants to know the name of the data set that holds the solution for fixed effects, It wants to know the name of the data set that holds this above table. It wants to know the name of your predictor variable, the name of your moderator variable, where the moderator is centered, what the interaction is called, and what order in the fixed effects it is listed. So the definition of each of these is given inside the regions program as part of the downloadable files for this example in SAS. And once you run this little piece of code, it generates this output. So it says the grip strength slope will be significant at the centered values of age below the lower bound and above the upper bound, which translate into the uncentered lower and upper bounds. Okay, why? So let's focus on these numbers right here. 70 and 82 are the cut points. So let me go back to the output for the grip strength slope that gives us the same information, and I'll go back to the SAS output because it's easier to read. 70 and 82. So what we just learned is 82 is the age at which the positive grip strength slope is predicted to become non-significant. So we knew that it happened somewhere between 80 and 85 based on these results, so we just learned that it's 82. So if we follow this trend, if this slope becomes less positive as age decreases, eventually it's going to be negative. And so we found that if you hit age equals 70, it becomes significantly negative. Another way of saying that is to look at the picture. So here's the picture in Stata, for instance. The grip strength slope is what we're talking about right now. So the red line is for grip strength age equals 85. We just learned that the point where this slope becomes significantly positive happens like between these two. But if you sort of follow this arc up past the blue, eventually it would become significantly negative, and that happens at an age of 70. So the grip strength slope is significantly negative below age 70, non-significant between 70 and 82, and significantly positive after age 82. And so in considering what to do with this information, you'd want to know, okay, well, where are my people? In this particular sample, there is no one below 70 years. So there are no people in this sample for whom the grip strength slope is predicted to be significantly negative. I think in Chapter 2, I report that there's about half of the people in the sample that fall into this range, where the grip strength slope would be non-significantly positive, and the other half fall into this range, where it would be significantly positive. So for half the sample, grip strength matters in a positive fashion. If we do the same thing in reverse, look at the effective age with grip as the moderator, then we get the regions of 9 pounds of grip and 18 pounds of grip. So going back to the picture where we have the effective age now is the thing we're focusing on. After 9 pounds of grip is where it becomes significantly negative, and if we were to follow this arc out up to 18 pounds is where it would become significantly positive. And again, the question is, where do the people fall in this sample? So we would want to report those values in conjunction with the distribution of the moderator to make sense of this. And so here are some words that I use to describe all of these things. And so this is taken almost directly from Chapter 2 of my book with very slight modifications to fit this example. And there you have it. So thanks for watching. I hope this has been helpful. Stay tuned for videos to be posted for example and lecture 7, which is addressing interaction terms that involve more than one fixed slope, which is necessary whenever the variables you're interacting each take more than one slope. So that's it.